Okay, hi Year 12. Moving down into our notes, we're now looking at the fundamental theorem of calculus, which relates to exercise 4C. So if you have not completed the previous exercise, and we're doing them out of order, if you haven't done 4E, that was the first one we did, and if you haven't done 4A, you need to go back and do those. In particular, actually no, both of them, because both of them have groundwork relating to this, so you'll need to do those first, please. Okay, so let's have a look at it. Mathematicians found a link between finding areas under curve and the primitive function. This made possible a simple method for finding exact values. So what we're actually doing when we're integrating or finding the integral or finding the primitive function, they're all the same thing. We're actually finding the area under the curve. So if this is our curve here, or our function, if we are finding the primitive of that function, of x in relation to x, that's all our dx is saying at this point, is in relation to x, and we're finding the area under that curve bounded by whatever values we give you, x values that is. So here we're bounded by b and a, b being the bigger number and a being the smaller, so b is what we call the upper limit and a is the lower limit. We will find that the curve, the lines relating to a and b, the x lines, x equals a and x equals b, and the x-axis, the area bounded by those four parts is the area under the curve, and that's what we find when we're integrating that. And this is the more formal method of explaining it. So the area enclosed by the curve y equals f of x, the x-axis in the lines x equals a and x equals b is given by this. We've got our integral between b and a of our function in relation to x, we say is equal to big f of b minus big f of a, where f of x is the primitive function. So the primitive function at b minus the primitive function at a. So what we do is we integrate our function, and then we substitute in our values into our integrated function of b, and then we take away what our value would be when we substitute a into that primitive. And that's what we're going to do today. The primitive function is what we've been doing in the last couple of lessons, and the rule will still stay the same. Oops, sorry, I'll slide down here a little bit. Okay, so what we do when we're finding the integral between two values of x of a function is we integrate it, and then we put our answer in square brackets. And what we do is we pop these two values at the sides of our square brackets, and then we substitute in the b, or the top value, in our bracket, and we take away what is subbed in when we pop our a in. And that answer is our solution. These are giving us definite answers, so we're not needing to add a plus c on the end here because we have values. If we didn't have those values, then we would be popping in a plus c, and it would be what we'd call indefinite. So let's work these out. So here's our first question here, and I'm going to work through this with you. So we're finding or evaluating this question here. And what that means is we're integrating or finding the primitive, that's what that symbol means, in relation to x, between 4 and 3 of this function. So we're going to do it with each other lesson we've been doing this week, is we're going to do this in parts. And my answer, in this case, is going to be in square brackets with my 4 and my 3. And my integral, once I integrate it, is going to pop in here. So we're going to add 1 to the index. Oh, I've already got my 2 out the front. I'm going to divide by that new index that I've added to, minus x. This one becomes x. So just to simplify it, I can actually get rid of those 2's. So what I will have, inside I will have x squared minus x between 4 and 3. So what I'm going to do first is pop in my value of 4 into what's in here. So I'll end up with 4 squared minus 4. That goes in first. Take away, I'm going to pop 3 in. 3 squared minus 3. You'll need to be really careful of your negatives, because when we're popping these values in here, between them, we want a minus. But I've already got minuses in there, so just be careful that you pop those bits in brackets. So what have I got? I've got 16 minus 4, which is 12. Take away 9 minus 3, which is 6. My answer is 6. Okay. Here's our next question. Question number 2 is asking us to find the integral, or the primitive, between 3 and 0 of 2x squared, and that's in relation to x. So I'm going to put my square brackets in there. I'm going to put my 3 and my 0, and now I'm going to integrate what's in here. So I've got a 2. I'm going to add 1 to my power on my index to get a 3. I'm going to divide by that new index, which is 3. I'm going to substitute my 3 in first, so I'm going to get 2 lots of 3 cubed all over 3, minus, pop my 0 in now, 2 lots of 0 cubed over 3, which is equal to, what have we got? We've got 3 lots of 3 up there, 1 down here, so we're going to have 3 squared, which is 9, 2s are 18. Take away, all of this goes to 0, which is 18, and that is our answer there. Okay, now scroll down past the blank page, which we may use in a moment, and down to the next part, which says the definite integral and its properties. So I want us to remember that when we are looking at the integral, or when we're integrating something, yes, we're doing it algebraically, but we always want to remember that what we're actually doing is finding the area under the curve. We're still doing that, we're just finding an algebraic way in order for us to find the solution, which gives us generally a more exact value. But there's some interesting things we need to take into account depending on whether they're odd or even functions. And that one is something that you might find very useful. Okay, so let's have a look at our first one. Okay, so here's a function here. It is an odd function. Okay, so we've got the same amount of our graph or our function above the curve as we have below the curve. So if we were to find, looking at down here, the integral between a and minus a of this function, we would find that that would be 0 because this part up here is positive. Oops. And this part down here is negative, and they're basically cancelling each other out. Okay, so I've got a positive and a negative, the same thing, they'd cancel each other out. So that's what's happening with an odd function. Okay, even, slight difference happens in there. So here's our even function. It is probably a power of 4 function, and we're looking at that between a and minus a. So what we have is, on the top of the graph and the bottom of the graph, we're reflected about the y-axis when it's an even function. So this section I've coloured in green up the top here matches this section above the graph on the other side, and our bottom section matches the other section there. So if we're integrating this function between a and minus a, what we could say we would have, it's just going to be 2 times our function between a and 0 because we have an even function. So what's above, sorry, not what's above, what's on the left side of our y-axis is going to be the same as what's on the right side. So that's another important rule that we may find quite handy. Okay, so we're going to have a look at this. Saying sketch y equals x cubed, and then find the integral between 1 and minus 1 of x cubed. Now, I've actually done this one already for us. So let's have a look at what we've got down here. So if you want to pause that and sketch y equals x cubed for me, what you're going to get is this picture along here. And we're looking at it between 1 and minus 1. So what you will find is this section here matches this section below the y-axis here. So we have a positive and we have a negative. So what we would be doing is, if we're finding the area under the curve, this one would cancel out this one here, and we'd end up with 0. Let's have a look what we'd have over here. To the right over here, we've sketched y equals x squared, which looks a little bit like this, and we're looking at the integral between 2 and minus 2. And what we would find here is this function is an even function. So this integral would be the same as the integral between 0 and 2 doubled. And that's what I've popped in there. I've just changed my 2 and minus 2 to a 2 and a 0 and doubled that. And that's what we can do with an even function. So popping our x squared, integrating our x squared, we're going to add 1 to the power. We're going to get x cubed. We're going to divide by that power, which is 3. I'm going to pop my 2 in here. So I get 2 to the power of 3. Take away 0 to the power of 3 over 3. So what I end up is with 2 to the power of 3 is 8 over 3, and I've times that by 2, so I get 16 over 3. So scrolling down a little bit further, what we end up with is this rule along here. We're looking at multiples of functions. And this one is one I actually just used up above without thinking, because I like to use this rule a lot, if we were to have the primitive of k times function x between the upper limit of b and the lower limit of a, what we can do is pull that k, which is a constant, out the front and pop it out here like this, and just integrate the rest of the function in relation to x between those same limits. So that k can just come straight out the front, and we don't need to deal with it over and over again. We can just do it straight at the end. Okay, so we're going to evaluate this expression. So we're integrating 5x squared between 2 and 0 in relation to x. So we are finding the area under the curve of a squared parabola that has a 5 out the front between 0 and 2. So we're looking at half of a graph of an even function. So we're looking at the right-hand side of the y-axis. But we don't really need to know that because we know what rules we can do. So I'm going to pull the 5 out the front to make it a little bit easier and just write it like this. And what that allows me to do is to leave that 5 out the front of these brackets when I do find the primitive, so I don't have to deal with the 5 twice inside when I work things out. When I pop my values in. I don't need to deal with the 5 twice. I can just do it once. Okay, so let's work out the primitive of x squared. It becomes x to the power of 3 all over 3. And what I can do now is pop my value of 2 in and then my 0 in. So popping 2 in, I get 2 to the power of 3 over 3. I'm going to take away, popping my 0 in, 0 to the power of 3 over 3. 5 can stay there for now. 2 to the power of 3 is 8 over 3. This part here goes to 0. So I get 40 over 3 as my answer. Okay, let's do the next one. Okay, so I've done this a little bit backwards because this, I've preempted myself, and I'm going to pop this 5 straight in here. And it actually, I guess I want to show you the difference. So let's leave the 5 in there, and we're going to use that inside our integral there to work it out. So let's integrate this one here. So we're going to have 5 times x to the 3 over 3, and that will be equal to 5 times 2 to the power of 3 over 3. Take away 5 times 0 to the power of 3 over 3. So what that means is we've got 2 to the power of 3, which is 8 5s are 40 over 3. Take away 0, which is 40 over 3. So what you can see there is whether or not I bring my 5 out the front like this or I leave my 5 in there, we're going to have the same answer. This way is probably a lot easier because the 5's dealt with right at the end. Well, here we've had to do the 5 twice. Not too much of a difference, but you might find down the track that that is a little bit easier with the pulling that the factor of 5 out the front. Okay, so there's another bit I want you to have a look at. So if you jump down to your next section, which is a blank section in your notes, we're going to have a look at this inequality. Not coming up too often, but something I think that's important for us to have a look at. So it says if a function f of x is less than or equal to a function g of x in the interval a to b, so we're between a and b, then the primitive of f of x between a and b is less than or equal to the primitive of g of x between a and b. So we're just going to have a look at the question below, okay? And I've pulled that from exercise 4C, question 12. So it's one of the harder ones, and it's using this inequality rule, and we're going to do a little bit of investigation work. So it says on one set of axes, sketch y equals x squared and y equals x cubed, clearly showing off the points of intersection. Okay, at first glance, you'll probably think y equals x squared and y equals x cubed only intersect at 0, 0, but I'm pretty sure we're going to find there's another intersection. So let's pretend it's a simultaneous equation and find where they intersect. So where x cubed equals x squared. Let's do that. So x cubed minus x squared then will be equal to 0. Let's factorize out an x squared, and we get an x minus 1. So where they're going to cross is x is 0, and x is equal to 1. Now that's going to help me draw a graph of these. So let's do that now. Okay, so let's go y equals x squared. And we might just pop a point 1 in here. and we're going to have a 1 here as well. And where these curves are going to cross is like that, and like that. And that's my y equals x cubed. So we have sketched that graph, okay? And we've shown our point of intersection here, and that's going to intersect at 1, we've worked out here, and at 0 here. When x is 0, y is 0. When x is 1, y is also 1. So that's our point of intersection. Part B says to hence explain why 0 is less than or equal to the integral of x cubed between 1 and 0, which is less than the integral of x squared between 1 and 0, which is less than 1. So let's have a look at what that's saying. So 1 and 0 is where we want to be looking at. So we're looking at there and there. So if we just grab a different colour, pink. So we're looking at in here and in here. So if we blow up there, we're looking at the area. So we know the area under our x squared is going to be bigger than the area under our x cubed. We know that part. Let's see what we know about this. So in order to answer this part here, we're going to need to use our rule up here. And our rule says that if a function x is less than a function g of x, if a function f of x is less than or equal to a function of g of x, then the integral of f of x is less than or equal to the integral of g of x between those two closed points. So we have our closed points here, our 0 and our 1. So what I can state there, that since by our graph, f of x, which is our x cubed, I'm going to say x cubed, is less than or equal to x squared in this domain. So between here and here, our curve of x squared, which is the red line, is always bigger than our curve of x cubed, which is the blue line. And that's what we've said, okay, in that range. That's what's happening. Therefore, in that same range, x cubed is less than or equal to the integral between 1 and 0 of x squared. We know that, okay? That's our area under the graph. What we can also say then is it's bigger than 0, because here's our 0 line along here. Oops. And it's less than or equal to 1, because here's our 1 across here. So we can explain it like that if we like. It says check the inequality in part B by evaluating each integral. So we're going to do that now. Let's evaluate this integral to start with. So we are going to pop our square brackets in there, and we end up getting x to the power of 4 over 4. Popping our 1 in, we get 1 to the 4th over 4 minus 0 to the 4th over 4. So we get a quarter minus nothing, which is a quarter. So that's the area under our blue x cubed curve in there. Let's now work out the next one. So let's work out our integral between 1 and 0 of x squared in relation to x. And we are going to get, popping our square brackets in there, x to the power of 3 over 3. So we will end up with 1/3, because 1 cubed is 1. We'll leave that like that. 1 is 0, which is a third. Now, this is true and backs up our information before. So 0 is less than or equal to a quarter, which is less than or equal to a third, which is less than or equal to 1. That's a good start for this exercise 4C. I want you to go and have a go at that now and bring any questions in to me.